So we've talked about the energy, the electrical potential energy a point charge has because it's near another point charge. Let's talk about just the electric potential of a point charge. Now, as I explained before in a previous video, we talked about electric field being a way to describe how a charge affects the region of space around it. And we defined that as the electric force a test charge or probe charge would experience divided by that charge. And we learned that the electric field due to a point charge, I ended up writing it with a capital Q. It can totally be lowercase q. When I explained electric field before, though, my way of distinguishing between the charge creating the electric field and the one experiencing the force was the capital Q was the charge creating the electric field, lowercase q was the one that would experience the force. Well, similarly, electric potential, not energy. So without the word energy, not energy. V is the symbol we are using. And the electric potential has been defined as the potential energy a point charge would have because of where it was in the electric field divided by the energy, the charge of the one we're talking about having energy. So for example, let's say I have this capital Q right here. We know it is creating an electric field that's pointing radially outwards, three-dimensionally. I just can't draw three-dimensionally particularly well. A small charge, Q, would totally feel a force in the direction of the electric field if it was placed in this region where there's an electric field. Now, I've only drawn 4 electric field lines, but keep in mind there's a whole lot of them. I'm just being lazy and not drawing a whole lot of them. So even if our little charge, say, was placed down here, it would experience an electric force because it's near this other charge that's creating the electric field. So the electric field just gives us a way to describe what Q, this capital Q, what effect it has on the region of space around it. Lowercase q represents the charge that feels the force because it's near capital Q. If it feels a force, it also has potential energy because of that interaction with the capital Q. The potential energy it has, we talked in a previous video about the potential energy a point charge experiences because it is near another point charge. That equation was K, Q1, Q2, so the two charges involved, divided by R. K is still our constant that represents the 1 over 4 pi epsilon naught. Q, lowercase q and capital Q are these two charges that are repelling each other in this case because they're similarly charged in terms of signs. And R is this distance, just that straight line distance between the two of them. Well, if we come back to this relationship of how we are defining electric potential, and I put in, my computer's having some delays. So I'm putting in the potential energy equation we already derived, but then I'm dividing by this charge, this lowercase q that's feeling the force, that has the energy. Now, granted, the other charge would feel a force and have energy as well, but we can only talk about one of them at a time. So if you remember just back to forces, way back in Physics 1, we had to consider the object that was experiencing the forces, and then we could use Newton's second law to talk about the acceleration of that particular object. And then the forces were always caused by an acting agent. So there was always two objects involved, but we focused on just one of them at a time. And that's what we're doing here as well. We have two charges involved, but we're specifically saying this lowercase q is the one that feels the force right now. It is the one that has the energy. Coming back to this equation, that little test charge, probe charge, disappears, and we find that the electric potential at that particular location, so this distance r, there's a voltage value or electric potential value that depends on how much charge we have creating the electric field, and then how far away we are from the charge. This equation is specific to point charges. It will also work outside of a spherical charge distribution, uniform charge distribution, and that's because the electric field we found outside of a sphere of charge had the same equation for a point charge. So R would be measured from the center in that case. So measured from the center of the sphere. So this equation is limited in that regard, but that's okay. What this is essentially telling me, let me draw a clean picture. If I have my capital Q that's creating an electric field, I'm going to draw more lines this time. It's telling me that any distance r to a point out here. So there's nothing at this point. It's just a location in space. If I go out the same distance in any direction, to a point in space, these points will all have the same potential, meaning I have an equipotential surface. Meaning the same potential value. Potential is measured in volts. So sometimes we just say it has the same voltage value. And ultimately that tells us that any charge placed anywhere on this surface, any Q placed on this surface will have potential energy because of where it is. The potential, the electric potential, this voltage, is a descriptor of where in the electric field we're talking about. In the case of this capital Q in the middle, we're just saying the same distance away in any direction is going to have this same effect on space, essentially, the same voltage value. So my little Q can be placed anywhere on this surface, and it will have the same amount of potential energy because of capital Q. Now, mind you, this equipotential surface is spherical. I just can't draw spherical particularly well because the electric field points radially outwards in all directions. So there would be lines coming out of the screen, going away behind the screen. And that means we could be out of the screen the same distance r and end up with the same amount of energy by placing a charge on there. So equipotential surfaces around a point charge are spheres. If I draw another equipotential surface, everywhere on this surface, which again is going to be spherical, it's going to have the same V, so the same electric potential value everywhere on this surface. It's different than the first one I drew. So if this new one I drew is a V1, I would want to label the second one I drew as a V2, or I could interchange 1 and 2. They have different values, but what we find is a point charge placed anywhere on the equipotential surface is going to experience or have the same amount of potential energy, regardless of where on the surface it is located. The beauty of equipotential of potential is that it's not a vector. This is a scalar. It can be positive or negative. I mean, it's going to be negative if we have a negative capital Q. So Q determines whether we have a positive or negative value. So if I happen to have multiple charges, let's say I have a 10 nanocoulomb positive charge, a 8 nanocoulomb negative charge, and these are, 4 centimeters apart. If I wanted to find the electric potential, or just potential, down here, the tip of an equilateral triangle. So these distances are all 4 centimeters. I simply need to add the voltage from charge 1, or the potential of charge 1, to the potential of charge 2 to have the total potential down there. The beauty is that it's not a vector. If you remember vectors, the electric field due to the 10, that wasn't drawn very well, but it would point away from that charge. It would have X and Y components. The electric field due to Q2 would have X and Y components. To find the total electric field, we would need to write those vectors in terms of their X and Y components and add them together vectorially. But because potential is a scalar, we simply plug in numbers. So we mean KQ over R, this equation for a point charge, plus KQ over R for the second charge. And this will give us the total electric potential. So K, I'm going to pull out because it's in both terms. Q1 is 10 times 10 to the negative 9 coulombs divided by the 4 centimeters. And then Q2, though, is negative. So I do want to put in the negative value. It just means a lower value. This is also 4 centimeters away. Scroll up just a little bit. So plugging these in, the total voltage at that point in space, I'm getting 449.5, which we have at best 2 sig figs, so 450 units. This is newtons meters squared over coulombs squared. Both terms in here are coulombs per meter. So 1 meter is canceling, 1 coulomb is canceling. That leaves me with newtons times meters per coulomb, which is a joule per coulomb. That's perfectly valid. We also call this a volt, though, and use V. So 450 volts would be the way to describe that particular region in space. So this location right here, there's nothing there. There's no charge there. This is just describing this particular location. If we wanted to place a charge there, we could totally now find the energy it has and multiply by this voltage to figure out how much energy a charge here would have if we put a charge there. But the original approach, there was no charge there. There was just a location in space. We were trying to find the electric potential. We can add up electric potential for however many point charges we have. Which means also, if we have I'll go all the way up there, continuous charge distribution. Like a line of charge. With linear charge density lambda. Let's say our line of charge lies on the x-axis. And we want to know the potential at a dot up here. So things we would need to know. We would need to know this vertical distance. I'm going to call it B. We would need to know how far the left end of the rod was from the origin. We would need to know the length of this rod or line of charge as well. So assume we know B, A, L, and lambda. And we want to calculate or determine the electric potential at point C. I'm going to call this point C, that dot I drew in the drawing. Now this I can see might incite a little bit of anxiety. That's not my intention. Before, in the previous section, we learned that we could find the total electric field due to a continuous charge distribution by adding up the electric field that each piece of charge created at that location, which we ended up needing to treat our line of charge as a whole bunch of little pieces of point charge. We had to write dq, r hat in terms of the same variable and then integrate. Well, this is similar here, but one wonderful thing about it is potential is a scalar. if I come over to my picture and I imagine this line of charge is made up of a whole bunch of little tiny DQs. I'm only drawing a few. Each of these DQs is creating a dV, a potential at that point because of the charge. They're creating different amounts of potential though, because they're differing distances away. Potential though is a scalar. It is not a vector, which simplifies this immensely. So we take the equation we have for V of a point charge that we just used. So V of a point charge, electric potential of a point charge, KQ over R, and we are going to add up all of these little pieces of charge based off of a variable R. So really, since we do not have vectors here, we just need to get dq and r in terms of the same variables. We need these in terms of the same variables or variable. So coming back to my picture, if I think about this leftmost piece of charge here, it is a distance, not of A, but some horizontal distance x to the right, and a distance of B below the point we are interested in. So R, that straight line distance from our piece of charge to the point we're trying to find the potential at, is simply going to be Pythagorean theorem, square root of x squared plus b squared. B is the same for all of these, right? This piece of charge down here, the far right one I drew, still has a horizontal distance of x, but x is different for both of these. But B is not. That vertical distance to get up to the point is the same. So the aspect of R that's actually changing is the x, that horizontal distance. That means we want to write dq in terms of dx. Our variable and our d whatever in our integral have to be the same. If you recall, we related dq and dx or dy through the linear charge density. We can say that lambda is total charge over total length, or a piece of charge over the length of that little piece. I'm calling the length of any one of those little pieces of charge dx because they're on the x-axis. If I solve for dq, I get lambda dx. I'm just equating these two together. It could also be q over L times dx. I'm assuming we have lambda and not a q. That's why I'm leaving this in terms of lambda. There's no x or y direction. That's fantastic. That was actually probably the hardest part of setting up the integral for the electric field. Now, these are the only two pieces we need. So thinking of this equation over here, I'm going to put in for dq lambda dx in place of r, the x squared plus b squared. Our limits will be from the left end of the rod, which is located at point A on the x-axis, to the right end of the rod, which would be located at A plus L. If the charge is uniform, we can pull out lambda. K, of course, can be pulled out because it's a constant, regardless. So I still have my limits. Let me see how it's written. This is one of the equations on the back page of the test notes. it's written a little differently. So ours looks like this for this particular problem. On the back page of the test note, you have this. B squared equals natural log. Okay, so this is on the test notes, very back page. The dx tells me that x is my variable. That means a is a constant. Plus or minus here, we just have to match whatever we have in our particular integral. Since we have plus, we're going to match the plus under the radical on the result. So the result of our integral is the natural log of x plus the square root of x squared plus, I don't want a squared, our constant is b. So I want b squared. And I do need to evaluate this between a and a plus l. But once I do, I have an answer. So remember, we were assuming we have a, b, l, and lambda. So now we have all the values. It's just a matter of plugging in the limits. So a line of charge, a thin rod, a wire, we can totally just treat it as a whole bunch of point charges and integrate along the wire or thin line of charge. It's much easier than the electric field integration simply because there's no direction associated with it. Okay, so point charge, V for a point charge specifically is this KQ over R. And by the way, this assumes V is 0 at R equals really far away, essentially, infinity. That's because we made that assumption for potential energy, that potential energy would be 0 for a point charge that was infinitely far away from another one. So we do have to carry that assumption through. So point charge, if you happen to only have a few point charges, like up here, we only had 2, just find V of them individually. If you had 3 or 4, I would find V of them individually and just add them up like we did here. The integration is if we have charge distributed over a longer distance, where it doesn't simplify down to just be a few charges. Okay. We'll talk about, what else do we need to talk about? Let's see. Some energy, and then we'll be finished with the chapter, actually.